Welcome back, everybody. We're going to look at section 2 or part 2 of our video in solving trig equations by factoring. I'm going to start off with a situation where it doesn't really look like one where you might want to solve it by factoring. But if we do a basic transformation on this trig equation, for me, I'm actually going to multiply both sides of this trig equation by the value sine x. And I'm doing that because I noticed that this is a rational expression. And if I multiply both sides by sine x, once that distribution takes place, it should reduce this fraction so that I don't have to deal with finding common denominators. One caveat that you should keep in mind is that you cannot multiply by a value 0 because that will violate the properties of equality. You can only multiply by values other than 0. So I have to satisfy myself in understanding that sine x could never be 0, but I'm guaranteed of that because if I look at this expression, if sine x were equal to 0 here, then this term would be undefined. So I'm going to proceed and go ahead and multiply by sine x. But if I do wind up with a solution that gives me a value that for which this sine function would be 0, I'd have to reject that answer. So I'm going to go through and solve this by distributing that sine x. I'm going to multiply the left-hand side, which will give me 2, and then sine x times sine x I can write as sine squared x minus, and then sine x divided by sine x will just give me 1. On the right-hand side, 0 times anything is still just 0. So now I've gotten a much nicer version where I don't have to deal with the common denominators and the fractions. I'll then solve it by isolation. I'm going to add 1 to both sides. Then I'll have 2 sine squared x equals 1. So I'll go ahead and also divide by 2 in that same step. So I'll get sine squared x is equal to 1/2. Finally, to help me isolate the value for sine, I am going to take the square root of both sides of this equation. When I introduce a root, I'm also going to have to account for the fact that there could be both a positive or a negative solution to this problem. So I wind up with sine x equals plus or minus the square root of 1, which is 1, over 2, square root of 2. You may recognize this in its rational form. This is another way of writing this is plus or minus the square root of 2 over 2, which we could obtain by multiplying by root 2 over 2. But I mention that because it makes it a little bit easier to identify the reference angle for this problem. So I know that when sine is root 2 over 2, I have a reference angle of 45 degrees, which, since in this problem I'm looking for a radian answer, I'm just trying to solve on the interval 0 to 2 pi, I'd write as pi over 4, the radian equivalent of 45 degrees. Next, I have to consider in which quadrant sine is going to be positive or negative, but that's actually what's kind of interesting about this problem. I could use the acronym A-SMART trig class to figure out which quadrants I'm going to be in. Where sine is positive is in the first and the second quadrant, and then where sine is negative is actually in the third or the fourth quadrant. So in this problem, because I have a plus or minus, I could actually be in any of the 4 quadrants. So I'm going to wind up with 4 answers, all of the basic answers that involve pi over 4 have a reference angle. So in quadrant 1, that's pi over 4. In quadrant 2, that's going to be 3 pi over 4. In 4, it's 5 pi over 4. Sorry, in 3, it's 5 pi over 4. And in quadrant 4, it's going to be 7 pi over 4. So those are my 4 basic answers. Again, to figure out exactly how to get these values, you can go back to our previous video on solving basic trig equations in radians, and you'll see exactly how those reference angles pan out. Okay. Another advanced technique that you can use in solving trig equations by factoring is if you have to factor by grouping. If you remember in grouping, I'm basically going to look at a combination of terms and factor them individually. So in this case, my leading terms have a common factor of 2 sine squared. So I'll factor a 2 sine squared out of my leading terms. When I do that, I'll be left with a factor of 2 sine x plus 1. And I can double check my distribution. 2 times 2 would give me 4. Sine squared times sine would give me 3 factors of sine. And 2 sine squared times 1 is itself. So that checks out. And then in my second grouping, it looks like there's a common negative. And I don't see anything else common there. So I have 2 sine x plus 1 equals 0. Well, that's worked out well for me because now I have a common factor of 2 sine x between each of these terms. So I can take that out. So I have 2 sine x plus 1 as a common factor. And when I factor that out, I'll be left with 2 sine squared x. And then really there's a coefficient of 1 here. So it'll be minus 1 equals 0. Well, we've successfully factored it. So now once I have it in factored form equal to 0, I can use the zero product property. So either sine x would need to be negative 1/2, because that value would make this term equal to 0. Or I could get sine squared x equals positive 1/2. And as we saw just a moment ago, if I take the square root of both sides, I would get that sine x is equal to plus or minus root 2 over 2 as a result of that. Okay, so those are my values for sine, but I still haven't solved the problem because I'm trying to solve for the values x on the interval 0 to 2 pi. So I'm going to need the reference angle for each of these situations. The reference angle for 1/2 would be 30 degrees, or since we're talking about radians right now, it's pi over 6. And the quadrants in which sine is negative, I go back to my A-Smart Trig class reference, and I'm going to note that sine is negative in the second and third quadrant. Third and fourth quadrant. My mistake. So I'm going to be in quadrant 3 or 4. So that'll give me either pi over 6, 7 pi over 6 in quadrant 3, or 11 pi over 6 in quadrant 4. So those are my first two answers. Now, because this is plus or minus, I'm going to expect about 4 answers from this. We actually solved this in the last problem, so we know that it's pi over 4 is the reference angle. And it could be in any of the 4 quadrants. So that's going to give me pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So there's a lot of answers to this problem. But the main takeaway is that we can basically factor this by grouping. Once we've broken it down by grouping, we can use other methods that we've developed up to this point to answer that question. Okay, I'm going to go through one more example involving tangent, and this is really factoring with the AC method. Now, the AC method, you might remember, is turning a trinomial into a problem that you could factor by grouping by splitting that middle term into a convenient set of terms so that we can proceed that way. For this one, since it's written in a strange form, I'm actually going to put it right into standard form for a quadratic. I recognize it as a quadratic because I see that I have a squared term and a non-squared term, and I'm thinking of tangent of x as my variable here. So if I bring that 7 tan x over, I'll have plus 7 tan x minus 15 equals 0. It gives me 3 terms where the variable I'm thinking of again is tan x and one of them squared. That is, I recognize that as a quadratic, but my leading term is not 1. So that means I'm going to have to use the AC method. So I'm going to look for 2 numbers which add to the middle term, which is 7, and their product is that first term times that last term. And in the standard form of a quadratic, we call that the a and the c term, or the a and the c coefficients. So that's going to be negative 30, and that's where that AC name is coming from. So 2 numbers that multiply to negative 30 and negative 10 would be 10 and negative 3. And those are the 2 coefficients that I'm going to split that middle term into. Okay, so I'm going to have 2 tan squared of x. Then I'm going to use 10 tan x, so plus 10 tan x, and negative 3 tan x. And the reason I'm allowed to do that is 10 minus 3, well, that's just going to give me 7. So I haven't really changed this expression. I'm just re-expressing 7 as a combination of 10 and negative 3. Negative 15 is still there. And the whole reason I do that is so that now I can factor this by grouping. Looking at that middle, that front term, the front 2 pair, and the second pair, if I go through the grouping process, the common factor in my first term is 2 tan x. If I factor that out, I will be left with a factor of tan x. The product of these two would give me tan squared. And then if I'm taking 2 out of 10, that'll give me 5. In my second grouping, it looks like I have a negative 3 that's common. And if I factor that out, I'm left with tan x plus 5. Tan x plus 5 is now my common factor between these 2 terms. And if I factor that out, I'll get tan x plus 5 times, factored from here will leave me with a 2 tan, and factored from here will leave me with a negative 3. Okay, we're almost there. So that was the advanced factoring technique. Once we've gotten it to here, I'm going to clean this 0 up, but once we've gotten it to here, we can basically use the zero product property. One of these 2 factors has to be 0 for this to equal 0. So either tan x is equal to negative 5, or tan x is equal to 3/2. Now, neither of those are special ratios for tangent, so I'm going to have to use a calculator, and I'm going to have to use the inverse. So I'm going to infer this in a couple of ways. So to get the reference angle when it's not a special angle, I need to use the inverse. So I'm going to use tan inverse. And to get the reference angle, I only really need to look at the ratio itself. In this case, that being 5/1 or just 5. The negative, I interpret the quadrant from. So the two quadrants in which tangent is negative, a smart trig class. So tangent is positive in 1 and 3, so it would be negative in 2 or 4. So I could be in quadrant 2 or quadrant 4. Since I'm answering this question in degrees, to get that reference angle, I want to make sure my calculator is in degree mode. So I'm going to check my mode. I happen to be in radian, so I'm going to change that over to degrees. I'm also just going to move this calculator over so I can access all the buttons. Okay. And then I can go second, and then tan inverse is the second feature of the tan function. So I'll do tan inverse of 5. It gives me 78.7 degrees. Okay, so that's the reference angle, 78.7 degrees. Okay. To get the actual quadrant 2 and quadrant 4 answers, I'm going to have to put that 78.7 in quadrant 2. So I'm just going to note that that is here. So if that's 78.7, I'm going 78 degrees short of this angle, which I know to be 180. So I'm going to go to the calculator and do 180 minus 78.7. I have 180 minus 78.7. In fact, I'll point out that you can actually, as a little feature of this calculator, highlight that number, hit enter, and it will pull it right down for you so you can get the exact value. So it'd be 101.3. So that's that first angle right here, 101.3 degrees. So that's my quadrant 2 answer. There's a fly in here. And then to get the quadrant 4 answer, I'm going to do the same thing, but in quadrant 4. So that's 78 degrees, or 78.7 degrees, back from this angle, which is 360. These numbers are not writing very well on this pad. 360, so I'm going to go over to 360, 360, and subtract from that this answer, which I'll scroll up to obtain. So I get 281.3. Okay, so that's that quadrant 4 answer. That's my next one, 281.3 degrees. Okay, we're not quite done yet because I also have these ones that I haven't gotten to. So tan 3/2, I'm going to need the reference angle for that, which I can get from the inverse of 3/2. And then the quadrant in which tangent is positive would be quadrant 1 or quadrant 3. Okay, so let me go back to my handy calculator. I'm going to do tan inverse of 3/2. Gives me 56 degrees. So in quadrant 1, that's 56. And in quadrant 3, that would be that many degrees past 180. So that'll give me my two other solutions from the second set. So in quadrant 1, I get 56.3 degrees, 6, and 236.3 degrees. Gives me my 4 answers to this problem. Okay, so those are some advanced factoring techniques and a little bit of review of solving those basic trig equations. There is no other, this is the end of the second part for factoring using advanced techniques, and the other videos in this series you'll find is solving using trig identities. So before you move on to that section, you may want to look at using basic identities or the derivation of some of the basic trig identities. Otherwise, you might be a little bit lost.